this video, we're going to look at calculating the binding energy of americium-243. So I'm going to start by writing down americium-243, and then I'm going to look up its atomic mass, or its atomic number in the periodic table, and that is 95. So let's put that down. So what I need to discover from this is if I want to calculate the energy stored inside one nucleus of americium-243, I need to know how many protons and neutrons I would need to make this nucleus. So obviously I'm going to need 95 protons, and if I take the mass 243 and subtract the 95, that would tell me the number of neutrons. So I get 148 neutrons. Alright, that's important because it tells us the mass of a proton and the mass of a neutron in atomic mass units. Again, on some of your calculators, an atomic mass unit is listed as a plain U. Alright, so I have 95, and each one is 1.007825 for protons, and my neutrons are 0.008665. Alright, so I'm going to add those up. And so when I say add them up, I'm going to take 95 times 1.007825 plus 148 times 1.008665, and I'm going to keep all of these decimal places. So I get 245.0255795. Alright, and again, that is in AMUs. Alright, so that would be the particles. If I had all these little particles just kind of laying around here, and my goal was to make a nucleus. And now when we squish them all together really tight and they're all compacted and I made the nucleus, we need to know the mass of the combined nucleus. So again, I have to look it up, or someone maybe gave it to us. So I'm going to write that number down here. The mass of the combined nucleus is 243.0613373. So first of all, you can check yourself in that this number here, the mass of the particles when they're not combined, should always be bigger than the mass of the combined nucleus. So we have some missing mass, and the missing mass is called the mass defect. So to find the mass defect, I'm going to take this number and I'm going to subtract that number. So minus 243.0613373. And I find out that my mass defect, so say mass defect, is 1.9642 AMUs. But I need to change that into kilograms. So I'm going to go into my calculator conversion menu, and I'm going to go into mass, and I have my answer in AMU. See, my calculator has an AMU. Many of the new calculators have just a plain U here. So AMUs, and I'm going to convert that into, whoops, where is my kilograms? Right there. This many kilograms. So I am going to round off slightly here. So 3.262 times 10 to the negative 27 kilograms. Alright, to calculate the binding energy then, I'm going to use Einstein's equation, E equals mc squared, where m is the mass defect, so in kilograms, times 10 to the negative 27. Obviously, c is the speed of the light, and I got to square it, and that's going to give me my energy, and that energy will be reported in joules. So I'm going to take that number on my screen, times 3 to the 8th, but I'm going to square that, and I get an energy of 2.936, I'm rounding off slightly, times 10 to the negative 10 joules. And again, depending on what number you put in here and how many decimal places, we could end up with very different answers here. So that's okay, just show your work. And then I'm going to go into my energy menu because it's more common to take that number in joules and to convert it to electron volts. So here's my electron volts. That's a lot of electron volts. I'll write the number down. 183,238,2393.46 EVs. So I'm going to change that into mega EVs. In mega means a million, means times 10 to the negative 6, so it means move my decimal point over 6. So 1, 2, 3, 4, 5, 6. Or you could take the number on your screen, which is your EVs, and divide by 1 to the 6th power, because that's a mega, and get 1832. So 1832 I'll round it off to 4 mega EVs of energy is in one nucleus of an americium-243 isotope.